Hello everybody, welcome to this recording of the Forces online tutorial. This is the first of two tutorials. We are going to look at equations, acceleration, how that affects motion and velocity time graphs in this tutorial. And I just thought before we started, you might just be interested in seeing this little word cloud. I did a survey of teachers who didn't have teachers of physics without physics degrees, and just asked them why they enjoyed physics, and they enjoyed the challenge, the problem solving, the logic and the fun. Then I asked them why they thought their pupils enjoyed physics, and they actually came up with different reasons, which I thought was slightly interesting, really. So they really felt that their pupils enjoyed practicals, but I also think that maybe some of this sort of problem solving, which is very apparent in Forces, is actually something that your students will enjoy, certainly some of them, hopefully. So just really thinking about equations and maths and questions like this. These are everyday questions that affect your pupils' lives, your lives, very much in the forefront of our minds at times. Different problems, and what about them? Why do we, how do we answer these? What do we need to know? And so think about this. What affects how long a kettle takes to boil? Well, you know, how much water is there? How powerful is it? What does a unit of energy cost when you have your TV on? And what does the TV, how long is the TV on standby, for example? These sorts of questions all use a mix of physics skills and math skills. You've got to think about what you're working out and find the values out of perhaps a question stem. Choose an equation, think about the units, make sure you're staying consistent with your SI units if that's relevant, which it usually is. Think about the math skills. You're substituting, or at least you're putting those numbers from the question stem into the different quantity in the equation. You're changing the subject or rearranging the equation depending on your language. Looking at powers of 10 using a calculator. So a mix of skills that your students have. So this idea is, this presentation even talks about equations and tries to get people who perhaps might panic a little when you see them, or might not be familiar with working with equations, to get you to understand they're not just letters. They're actually using words or symbols to tell a story that's relating to a physical quantity. And you might want to think of some examples that you use in real life. By all means, pause the video and then move on when you're ready. As well as using these words and symbols to tell a story, we actually have to put numbers in, and we're predicting, for example, will a fairground ride work? Will a space probe land on an asteroid? What's the range of the electric car? Can we compare an athlete's performance or the efficiency of appliances? Can we explain why automatic night lights turn on and why cars moving faster have longer braking distances? Can we calculate stopping distance, for example? So these are all things where we're putting numbers into our equation to tell that story. And you might want to look for some patterns. We've got three equations here that show proportionality. What we mean by that is if you double one quantity, you'll double another quantity. If you double frequency, then the wave speed will double. If you double velocity, then the momentum will double. If you double the mass, then the weight will double. You also have equations that show proportionality, but are also cumulative. If we look at how far we travel, by all means, doubling the speed will double the distance. But if you think about it, if we look at how far we've traveled in 1 hour, and then we double the time to 2 hours, we keep adding that distance traveled per hour into the value of the distance traveled. And the same with the energy transferred. If we have a kettle of a particular power and we leave it on for double the time, then we'll transfer double the energy. That's really what we're looking at. And it might help you to think about your numbers this way, or you might just say, fine, and continue the way you have been teaching. But sometimes when we point out some of these patterns, it can maybe help you choose perhaps a relevant or linked equation to help in the examples when you're talking to your students. So how do you introduce numbers in physics? And again, an inexperienced teacher, one who's not used to working with equations, might just really want to give a calculation to their students, ask them to do the question, and then be slightly puzzled why it doesn't work. And I absolutely hold my hand up, and I will say that I have been guilty of that in the past. A more productive way, perhaps particularly that will help to engage some of your students that are panicking when they see an equation, is to ask them just to describe what's happening, looking for a pattern. If you're trying to do a calculation that involves perhaps mass and acceleration, you might just say, well, what do you think is going to happen if I double the mass in this experiment? So just does the acceleration increase or decrease? I'm pushing by the same amount on this trolley, but I've doubled how heavy the trolley is. What do you think is going to happen to the acceleration? And they can probably tell you, well, you're going to have less acceleration because you've got the same push, but a heavier trolley. You can move on to qualitative. So just saying, does it double or does it halve? If I double the amount of push that I give, the force I give to this trolley, even though I've made no changes to it, will I double or halve or have the acceleration stay the same? And then finally, you can move on to those quantitative equations. So exactly as I've said, think about what I said in the past slide and look at this scenario. So I've been talking about forces, mass times acceleration, and now we're going to talk in a bit more detail about acceleration. So I've described it at the top in words, forces, mass times acceleration, and in symbols. It's a capital F for force equals MA, M for mass, A for acceleration. So conventionally, we'll use the units of newtons to measure mass, to measure force even. And 1 Newton would give a mass of 1 kilogram and acceleration of 1 meter per second squared. That same force, 1 Newton, would give a mass of 2 kilograms and acceleration of half a meter squared. That's what the equation is telling us. So you might want to just pause now and have a little think and see if you can come across some examples using that equation I've just been talking about, F equals ma. Now, formula triangles. I always ask my groups, would you use them? Do you use them? A lot of people do. So a lot of people tell me they do because their maths departments do. With anything like this, there are advantages and disadvantages. And I am not going to say to you they're spawn of the devil, which is a phrase, isn't it? You know, they're a terrible, terrible thing to use, because I don't think that's helpful at all. And they definitely do have a place. They are a useful shortcut if your students have learned the triangle in the right way and they've learned the technique for using them. And it is easy for your students to understand how to get an answer from using these. It can be they're taught because you've always taught it that way, you've been familiar with it, you stumbled on it with a weak group of yours, and now you teach it a lot using that. And I mean, it's certainly, if you have students with poor skills with algebra, have got low confidence using their maths, if you've got a low ability group that in terms of their maths that are approaching exams and it's really important they can just get some sensible numbers, I can see the logic. The reasons that we recommend you try and avoid them is that, first of all, students can get in the habit of using these triangles based on procedure rather than understanding the actual equation. So I've just been talking to you about the idea that an equation is telling a story, and the triangle doesn't back up the fact that that equation is telling a story. It really only works for simple equations which are multiplied together. And I know that people say, oh, well, I can use it for energy is mass times specific heat capacity times the temperature difference. I can use it for this, I can use it for that, but it starts getting pretty complicated. The other more important factor for you to think about is that you don't get any credit for writing an equation out in this form in an exam. So if your students had written F equals ma as in a line, or if they'd written force is mass times acceleration, they'll get their mark for using the equation. If they've drawn a triangle like this, they won't. And that means that your students really do need to be familiar with using that equation sheet to take the correct equation and write it out. So the other thing as well is that some of your students may well want to go on and do physics at a higher level. And if they don't develop these algebraic skills, you are potentially holding them back. As I say, swings and roundabouts, you'll use these in some situations, but hopefully fewer situations than you might do just by habit. Okay, so we have some examples. I would like you to just try these questions, pause the video, and then move on, and I will continue to look at some slides which look at the answers. So you can see the working out here. We've taken our equation F equals ma, we've substituted the mass 22 kilograms and the acceleration 1.8 meters per second squared. We've got our answer, and that squiggly equals just means it's approximately equal to 40 newtons. Just to say that our data here has been given to two significant figures, and therefore you wouldn't want your example to be given to any more than two significant figures. So you would really need to round up that 39.6 to be consistent. However, at GCSE, unless the question is specifically asking you to use the correct number of significant figures, you would be fine giving either of those answers. So by the end of the shot, we hope people will have loaded a bit more, but they won't necessarily push any harder. So if it's the same force, and you've got to be precise here, if they push with the same force, the net acceleration will decrease. If you end up, I don't know about you, but if you want to keep going at the same speed, you'll just have to push a bit harder. Okay, now work out the mass of the food they're buying. In other words, what has the change been in that trolley? So we're making some assumptions. We're making the assumption that the force hasn't changed. So we put in the precise number in this case to get our calculations. And then there is a second step to work out our change in mass. So 66 minus 22. You might notice that acceleration, 0.6 meters per second, is actually a third of what it was before. Previously, in the first question, it was 1.8 meters per second squared. Now it's 0.6. And so our acceleration has gone down by a factor of 3, and that implies a total mass of the trolley and food has increased by a factor of 3. Now think, we've got somebody sitting in a wheelie chair, you give them a shove, what happens if you push them for longer? Pause and just think about the answer that you'll give. Now, this is something I would like you to really pause and think about before you move on the video. How does the position of the ball change each second? So we've got somebody standing on top of a building, they drop a ball, the initial speed, they just release it, is 0 meters per second. It's going to move downwards because it's gravity is making it accelerate. Think about the fact that acceleration means your change in speed per unit second. It's a rate of change of speed, change of velocity. In this case, if it's moving in one direction, you could, particularly with a lower, a younger group, for example, use the word speed, though strictly speaking, acceleration is a rate of change of velocity, which is speed in a particular direction. So what you can see from that animation and I hope this is what you drew, is that the distance the ball travels every second increases. In fact, it increases by about 10 meters each time. I'm not sure. Yes, so we've got it's got the speed. So in 1 second, this ball has moved 9.8 meters, and now it is moving faster than it was before. So we've got the speeds here. So in that sort of second, it is moving at least 9.8 meters. It's not actually exactly that number, and I don't want to do the maths while we're talking to you, but you can see how its speed is changing, and therefore at the start of each second, its speed has increased by 9.8 meters per second. Meters per second. So the distance it will travel in the next second will increase because its speed has increased and is continuing to increase. You can see that acceleration in this context means the speed or velocity is increasing by 9.8 meters per second each second. Now we've got somebody, they're throwing the ball upwards. Can you see? And they're initially throwing up at 39.2 meters per second. How does the velocity change? How does the position change? Pause the video, have a think back to what we said previously when we were dropping the ball. This time we're throwing the ball upwards, and it's got its maximum velocity. I'll give you a hint at the bottom. When you're ready, move the video on. So what you can see is that ball traveling upwards is slowing down. So every second it is moving slower than it was the previous second. The distance it travels in each successive second gets less. And because the acceleration in this case is 9.8 meters per second squared, the velocity is getting smaller by 9.8 meters per second. So the ball is going upwards. The force of gravity is acting downwards in the opposite direction. So it's having a braking effect on that ball. And then obviously the ball's reached the highest point, it will then turn round and start coming down at the same speed. So as it in the relative positions. So if it's doing 9.8 meters per second going upwards here, when it turns round and starts to fall down again, it will be doing a minus 9.8 meters per second because now it's traveling in the opposite direction. And then its velocity will increase. So it'll be traveling at minus 19.6 meters per second, etc., etc. By all means, pause and have a think about what I've said. Now we're throwing our ball horizontally. Draw what you think will happen. There aren't any forces acting horizontally. We're going to pretend there's no air resistance horizontally. So there's only a force acting down, but our ball is starting to go across. Stop and think based on what you know about the way balls move and see if you can show how the position changes each second. Pause before you go on here. So what you will see, you can always sort of like pause this video, get a ruler. You will see that the distance between each of those dots going sideways is the same. It's not changed. But going down, we've got that increase in how much distance the ball travels downwards each second because it is accelerating downwards. And as well as speeding up downwards, the direction the ball is traveling in has changed. So two things have changed: the actual velocity, the speed, if you like, and the direction. And remember that velocity is speed in a particular direction. So we've got another equation here. We're actually looking at acceleration, and people can find this quite hard to think about. It's a rate of change. It's change in velocity over the time it took for that change to take place. you'd look at the starting and the finishing velocities, you compare them to work out the change. There is a delta sign. So in symbols, when it's drawn down here, it's A for acceleration is delta, which means change in, V, change in velocity, and delta T, which is time. Occasionally, particularly with what we call a Suvat equation, some of the equations for motion, we would say that V stands for the final velocity and U stands for the original velocity. So we could also see it written as A, acceleration, equals V minus U over delta T. Read this slide through and fill in the gaps. Pause the video and I will click onwards in a moment. Okay. Did any of these surprise you? Hopefully not. Just be aware. I should say the final one changes direction if the acceleration is basically in a different direction to its velocity. But we would see circular motion if the acceleration is always at right angles to the velocity. Okay. Have a look at these questions. Have a go. We're using the equation at the top, A equals delta V over delta T. Pause on here, maybe jot down the calculation, have a go before you move on. So what we've done, we've written out the equation, we've substituted in the numbers, and we've done the calculation. The harder question, we have the cheetah slowing down. That's why we would say the acceleration is minus 36. And now we're working out the time. So what we're doing is we are assuming we can, when we look at delta T, we can substitute time. As long as we sort of make an assumption that the acceleration is constant during the period of deceleration. So substituted that minus 36, that naught minus 27, and then we've got time T under there. You can see that the acceleration is 4 times greater than your answer to the first question. 36 is 4 times greater than 9. So your time will be 4 times smaller. That's one way of doing the question. If you can get your students thinking in this, if you like, I say qualitative, it's more that it's quantitative. So you are sort of getting this big idea of proportion there. Have a chat with your maths department. How do they rearrange or change a subject of equations? I certainly would say that doing it in this order, substituting first, will get more marks in an exam. If your student gets to this point in an exam, they then mess up for that final calculation, then they will lose that mark if they get the final part of the calculation wrong, but they will get credited for substituting correctly. That is a skill. And anyone who says it isn't, I think maybe hasn't sort of battled with a group of students who didn't know how to substitute. It is a skill. It is something we need to explicitly teach. We're now moving on just to look at some graphs, some motion graphs. So we've been using equations to describe the motion here. What happens when we're looking at the graphs? How can we draw it? So you've got a graph like this. So if you had this graph, we have time along the x-axis, we have velocity along the y-axis. You can describe what's happening at each stage. You can compare different parts of the graph, for example, section A to B and C to D. And I've used the word qualitative here. I mean, you might sort of say, well, it's not really qualitative, but it's not giving, it's more than just describing, but it's not as much as doing a calculation. And then quantitative. So have a little think about this. What else could you do with your students for this graph? And think about these 3 different ways of interpreting a graph. It might be that you want to get your students to do some sketch graphs, maybe of motion. You maybe want to discriminate within your group some of the ones that are very keen and able to move on very rapidly, or you might want to maybe get people to look at results from an experiment. But having 3 different ways of levels of detail that you're looking at a graph maybe can make it a bit less threatening for people who are worried. So this graph tells a story. It's the same graph. It tells you that as a motion graph, the velocity, the vehicle or whatever is getting faster. Then it travels at a constant velocity. You can read that it's 20 meters per second off the y-axis. Then it gets faster again. Now it's increased in 5 seconds between A and B. It increased by 20 meters per second. Between C and D, it increased, I'm looking at the change, by 30 meters per second in 5 seconds. So that's actually getting faster, even faster. And then here it's slowing down. And you could be a bit more descriptive. You can say it's getting faster at a constant rate. If you stop and think about something falling in midair, when you've also got the effects of drag forces, you actually might have a curve rather than a straight acceleration. Realistically, it's very unusual to have the acceleration being constant. Getting faster more rapidly. I wouldn't talk about a stronger acceleration. I wouldn't really talk about a faster acceleration. You have to be slightly careful, but I would talk about a bigger acceleration. And then we've also got a quantitative where we've done some calculations. So these are all levels you can talk to your students about. You can get them taking the same graph and having a discussion or doing calculations at different levels. The bonus, how far has it traveled? Now, a lot of students can tell me that that the distance traveled is the area under a graph. It can be tricky to work it out. And I should say, I haven't really ever seen an exam question ask you to calculate the whole area under a slightly complicated graph. It'll be quite a simple one. But if you did have to do that, you'd maybe be advised to split the graph. So from A to B, we've got a triangle. Area is half base times height. B to C, we've got an oblong or a square. From D to E, we've also got a triangle. Half area base times height. The little complicated bit from C, well, we've got 2 whole squares. I don't know if you can see my mouse, but you can probably see we've got an acceleration on top of an original speed that was not 0, and then we've got a triangle there, so you'd probably split it up. As I say, I would think this is actually stretching your students a bit. By all means, give them a go. Here are some answers. And always remember to add them up. As I say, I think it unlikely you would ever be asked about this. So thank you very much for sharing your time with me. Don't quite know why I've got this triangle here, but we will stop sharing now. I will stop presenting. Thank you very much for sharing your time with me and watching this video of the first tutorial. Please, will you, having watched it, email me, Nikki Thomas, at nikki.thomas@ogdentrust.com, or your tutors, to say, I have watched this, and then we can mark you down as seeing the register, as as completing this part of the tutorial. I hope the rest of the skipped program goes well, yeah, thank you very much.